Good morning, everyone. My name is Anastasia Riasanova, and I am a coordinator of the Treesearch Research Infrastructure. And I would like to welcome you all to our research infrastructure webinars, where we are presenting the available facilities and competences at different universities, which are part of the Treesearch. And today it's my pleasure to welcome the team from the Mid Sweden University, in particular Magnus Hummelgård, who is actually the node coordinator of the Treesearch Infrastructure at Mid Sweden University, and also Börje Norlin. So Magnus, please, the floor is yours. You are welcome to give us an overview of the facilities that you have.
Yes, thank you for having us. We have 5 different systems at this node at Mid Sweden University. And today we're going to highlight 2 of them. But I will also mention one slide each of the other 3 instruments. So we have a Electron Microscope, atomic force microscope, Raman spectrometer, this broad ion beam Miller machine, and a custom-built XRF machine. So the electron microscope we have is, what shall I say, optimized for low voltage use. It is an immersion lens system, and it can use backscatter detectors as low as 500 volt. It is quite rare. And the resolution is 1 nanometer at 1 kV, and it can work in a low current mode. That means less than 1 picoamp in beam current. So it is optimized for soft materials. Okay? That is a common key term in electron microscopy, sensitive materials for electron beam. It has a few different attachments. It has a EDS detector for standard elemental characterization, but it also has a software package, so you can do a particle correlation. So it can you can make an automatic routine, so it can go around and measure several particles that you have and make elemental composition mapping of each particle, and then you can get this what shall I say, matrix data and correlate particle size versus elemental composition and so on. It also has a lithography attachment, so you can do some nanoscaled electron lithography. And together with this machine, we have a iridium sputter for sample preparation. And this machine was installed in 2016. The atomic force microscope that we have, if some of you are not aware of atomic force microscopies, it is basically like a mechanical probe tool. It is similar to a stylus profilometer, but it's on the nanoscale size. So it's a miniature profilometer, you can say. This park system that we have is extremely easy to use. AFM is known to be tricky, but this machine is very easy and user-friendly. And part of that user friendliness is the very easy change of these scanning tips, because they are pre-mounted in this system, and that makes it, for the novice user, it becomes very easy to change tips. This is a known problem in the field. The advantages of this particular machine is that it has a very large sample size that you can use. Most AFM handles samples that are like 1 cubic centimeter or something like that in size. But in this one, you can fit something that is 200 by 200 by 20 millimeter. So we use this at Mid Sweden University for studying of electrode materials, and then we can use the whole electrode without cutting out pieces of it, so we can analyze it directly. Also, the scan range when you're scanning the images is huge in this machine. So we can scan 100 by 100 by 15 micrometer. That's the size of the images that you get. That is around twice the size of a normal AFM. And on top of that, this machine is fully configured for electrical measurements. So that means you can do basic conductive AFM measurements, electric force measurements, Kelvin probe force microscopy, but also more advanced stuff like scanning capacitance measurements and photocurrent measurements. So there's a laser attached to this system as well. System was installed in 2019. The third machine that we have is this Raman confocal microscope. So this is like two systems combined. So it is a optical microscope, but it has this Raman spectrometer attachment. So it is not just a Raman spectrometer, it is a spectrometer built into an optical microscope. The advantage of that is that you can measure on local sites. So I mean, basically, you can target selected areas across the surface that you are monitoring in the optical microscope and measure the Raman spectra from that. And the Raman spectra is what you can say it is the twin sister of infrared spectroscopy. So it provides similar information, vibration, energy information from chemical bonding. One thing that is a little bit extra on this machine is that we have a motorized stage on it. So that means we can program it to measure the Raman spectra automatically in an array of matrix. I mean, so you can scan an area across the surface and monitoring the Raman spectra on that, and that gives you a mapping of the surface that is very similar to this EDS technology in the scanning electron microscopy business. But here you get the chemical bonding information instead, but it works in the same way. So you could map your optical images in this machine. The laser that we have on this machine is a green laser. That is not so common. Most common laser is red. But on this one, we have a green laser of 532 nanometer and 100 milliwatts of power. So usually, where shall I say, the wavelength of the laser, the intensity of the Raman spectra is very dependent on the wavelength of the laser. It goes inverse proportional to the power factor of 4 of the wavelength. So the intensity becomes very, very small when you go towards the red light of the laser. So that's the reason why we use a green laser in this machine to boost the signal level. However, it also creates more fluorescence in the samples that you're investigating. So green laser is more for inorganic materials and not so good for organic materials. So that is a quick overview of the first 3 instruments that we have here at Mid Sweden University. So now I will talk a little bit more in depth on this broad argon ion beam miller. And that is not a machine that you use to study things. It is a sample preparation machine. So it is a tool that is used in combination with, most of the time scanning electron microscopy. However, it could be used also to some extent for optical microscopy, but it becomes a little bit overkill when you use it for those kind of tasks. And what's the purpose of this machine? Well, this machine is used for cross-sectioning a sample. So if you don't want to study just this, the upper surface of some material, but want to see how it looks on the inside, you want to make a cross-section of it. And there's several ways of achieving cross-sectioning of samples. One is mechanical grinding and polishing. And the alternative technique is to use some kind of plasma beam to what shall I say, etch away materials of the surface. And there are two types of plasma beams that you can use. One is called the focus ion beam, and that is a tool that is used inside the scanning electron microscope. And the other tool is the thing that we have on picture here, the broad ion beam tool. So they are basically the same kind of apparatus, but they serve different purposes. And the difference is that the broad ion beam can make a much broader cut. And we are talking about up to 5 millimeter in width of the cross-sectional area. If you compare that to the focus ion beam, it is usually less than 100 microns and things like that. So that is the main advantage of this machine, to get a nice atomic flat cross-sectional cut that is very wide and broad. And if you're studying like fibrous materials and papers and things like that, you really need that large field of view to get a proper understanding of how the cross section looks like. Otherwise, it will be like monitoring things through a pinhole. So that is the purpose of this machine. The strength when you're doing this kind of cross section with this machine is that because you have this plasma beam, it is very, what shall I say, mechanically gentle towards the surface. So we don't introduce any mechanical deformation as you will have if you grind it with the mechanical polishing. Then you will start to tear down fibers and things like that, or they start to become clamped and bent and things like that. So we don't have any mechanical side effects in this machine due to this plasma beam procedure. The con instead is that because we use this plasma beam, then we introduce heat into the sample instead. So if the sample is heat sensitive, then usually this is a no-go, because you destroy or burn off your sample. So it's not good if the sample is heat sensitive. It is a slow process. It's very sample dependent. It can take anything between 2 hours for a quick session up to 20 hours for these long run sessions. And usually you run this machine overnight. So this is not a tool that you want to prepare like 20 samples in. you usually you have one distinct sample that you want to test, and then you run that. And I would say most of the time around 4 to 8 hours is enough. The machine that we have here at Mid Sweden University, it's a Hitachi machine, and it's called the IM 4000 or IM Miller 4000, and it was installed 2016. So how do you do to prepare your samples in this machine? So the coming slides is to give you some kind of introduction of how it is actually done and what you need to do. So what we see here is that on the left image, we have a typical paper substrate that we want to analyze. And what you're going to do is you mount this paper substrate on a back steel support piece. That's the thing that you see in the picture here. And depending on the type of material that you're studying, more advanced mounting techniques can be used. But on this picture, it is just glued directly to the steel's back support there. You take this, the whole steel piece there is in the picture around 20 by 10 millimeters. So you have some understanding of the scale here. Then you take this mounted paper on the steel support and put it into this tool piece, and that is the big picture in the center there. So, and what the tool piece allows you to do is to make very precise adjustments of where you want to cut to position your cross section in your sample. So where do you want the cut to be? So that's what the tool piece is used for. So it makes very good possibility to make very good adjustments for that. But you can see in the front of that picture here, on front of the paper, we also see another metallic silver colored square, and that is the front mask that is facing the plasma beam. So the technique is quite simple actually. The plasma beam comes and passes over the titanium mask, and everything of the sample that is exposed above it will be blasted away. And the right image shows how the chamber view of the machine looks like, and when the tool piece is mounted in the machine. So you just put this inside the machine. Because it is an argon plasma beam, it will be evacuated to vacuum conditions here during operation. So if you sample has problem with vacuum, then it's not so good to use this machine. So when you mount the sample in this tool piece, this is a more detailed image of the tool piece. So you can see there's a lot of knobs and screws that can be used to adjust it. So what this tool piece allows you to do is both positioning the sample and positioning where the cut is supposed to be on the sample. And you can also rotate the sample and position the mask across on top of the sample. So you have control of all these parameters with this jig. And there's a dedicated microscope, and that's the thing we see here on the right here. So we put the tool piece inside this standard optical microscope, and then we can look inside the microscope to make this fine adjustment. Of course, this is done under optical microscope. So here we can see the disadvantage to a focused ion beam technique, where you have the scanning electron resolution of scanning electron microscope to help you guide where you want your cross-section area to be. So here it is an optical technique instead. So that means that the precision that you have here will be limited to these optical techniques. So we can see in this down here in the right corner, we see some image how it looks like inside the optical microscope, and that means you can see that the tolerances are in like tenths of microns. So within 10 microns you can adjust where the position of the cut will be. And what the images, this optical microscope images show is that you want to position the titanium mask so it covers the bulk of your sample, and only a small fraction is sticking out of and becomes exposed for the plasma beam. And there's a reason for that also. You don't want the width of the cut can be up to 4 or 5 millimeters. So that means that the plasma beam has a diameter of around 5 millimeters. So if you have several millimeters sticking up on top of the mask, then you will not make a nice clean cut. You will start to dig a hole, drill a hole through your material, and that is a no-go if you want to create a good result. So usually you make some kind of pre-treatment. If it's just a paper that you want to study, then you cut the paper with a razor blade, and that is the only thing that is needed for paper. And then you adjust this mask so you expose around 20 or 50 microns of paper. So the cross-sectional cut will come up to 50 microns below where you cut with your razor blade, right? So that is how you work with this machine. So if you want to have the cross-sectional further into the material, well, then you need to cut more closely with the razor blade, so you expose that area. And when you put this sample inside the machine, yes, that's the right picture here. You can see how it looks like. So now we see the back support piece here that's marked with D here in the picture. We can see the paper substrate marked with C here, just like a tiny little white line there. It's all barely visible. You use this optical stereo microscope also to check on the sample when it's in the machine. So in the machine it will become more easy to see what you're doing, but this is just a standard picture. You can also see the titanium mask that's marked with B here, and then we have the plasma gun marked with A on the left here. So when you start the machine, this front square piece is removed, and the plasma beam fires up and starts exposing your material. On the control panel on the machine, it is quite this machine is very simple to operate. So you don't actually have so much knobs to fiddle with. So you have 2 parameters basically or 3 parameters you can play with. The most important is the accelerating voltage of the plasma gun, and that is you can say that is the speed of the cannonballs that you're shooting. So if you increase the speed of the cannonballs you're shooting, you create more damage in the material, and that means that the cross-sectional time will be reduced. The process will go much faster, but it will also create more heat into the material. So that is the reason why you sometimes want to spend 20 hours doing the cut, because you're doing it at a lower accelerating voltage, because you want to protect the sample from not burning off. So that is the most vital parameter on this machine. The two other parameters is, of course, time. You can choose to wait longer time or shorter time, depending on, so it correlates with accelerating voltage. But the third parameter is the rotation of the whole tool piece. So in normal operation, you don't want the beam to come from just one direction continuously forever until you're finished. And the reason for not wanting to do that is that if your material is a complex material that contains both hard and soft materials, if the beam comes from only one line, then those hard materials can start to act like a mask themselves, and that will create a very uneven cross-sectional cut. So then you rotate the sample back and forth in front of the beam like this in oscillating motion. And how that oscillation is done, the oscillation angle and speed, that is a parameter that you can control as well. But when you reach this stage, it is quite easy to operate. You just program it like the dishwasher machine at home, and you set it to go, and you come back after a few hours and check how it is done. The machine automatically shuts itself down after the time you have selected. So if you have more complex samples, or what shall I say, more irregular shaped samples, I mean, it could be like you have a surface mounted components on circuit boards or something like that. Yeah, some more complex thing that you want to study. This machine has some requirements, and that is that every sample you're going to cross cut, you must have a completely flat, it must lie completely flat towards the mask of the tool piece. So if there are some cavities or holes between the sample and the mask, that will disturb the plasma beam and create a very bad cut for you. So one way of circumventing that, if you, for example, have like a circuit board that you want to investigate, then you must do a plastic resin embedding of the material first. So you basically mold a completely square piece out of it first, and then you make mechanical pre-cutting and pre-polishing of that little piece, and then you put that piece into this machine for the final cut. That's one way of handling materials that has rough surfaces, basically. So it doesn't need to be like surface mounted components. I mean, it can be like, let's say you have a electrode material that has a very rough texture on the surface and you want to study that, then it could be necessary to make a plastic coating of the surface to flatten it out. Besides cross-sectioning, you can also use this machine for surface polishing, and that can sometimes be quite neat. Surface polishing can be used for many things. One can be that you have a mechanical polished sample, then you can make the final touch-up of the sample by doing this plasma beam polishing, and that will give you that, so what shall I say, final flatness and smoothness of your surface that you have mechanically polished. But you can also use it like some kind of etching tool to clean up the surface if there is some contamination things on it, because it's a very, very gentle approach. So you're milling away a small piece of the surface. So the machine can be used for surface polishing as well. And you see that's what we see here in the picture. Also, there's a different tool holder for that. You basically mount the sample onto a cylindrical disc, and then you mount that cylindrical disc into a tube, and that is the brass colored thing that's around this disc in the picture. and that tube will act like the mask. So you have the angle of that whole setup is almost completely parallel to the beam. So the beam is just passing straight over the surface in a very gentle way. So this schematic picture is a little bit exaggerated. So it looks like 45 degrees, but most of the time it's like 1 or 2 degrees when you run this technique. So I will finalize this introduction to this broad ion beam tool by showing you 3 typical results that you can achieve. And the first picture we see here is a plastic coated paper that is used for, like, you know, milk boxes and things like that. They have a plastic coating on the inside to protect the paper from not becoming wet of the milk. So that's what we see here in the picture. So the dark top area here, that is the surface of the plastic that is coated on top of the paper. So we are only interested in the cross-sectional area, and that's what we see here in the centerpiece here. So, and the right picture is a magnified area of that section, so it's easy to see in the right picture here how the results look like. So this has been, what should I say, prepared with this broad ion beam tool. So we can clearly see that the plastic layer here on the cross-sectional area is very smooth. It doesn't have any real texture because it's a polymer. It's a completely solid. But beneath that, we can see the paper fibers, the actual paper that the plastic is glued on. So here we can see how the performance of the machine is. And as I said in the beginning, the biggest advantage of this machine is to create high quality cross-sectional areas that is very wide. So the left image only shows 1 millimeter. Remember, it is 4 millimeter long. So you have a very, very large, broad cross-sectional view. So the left image is still a subset of the real complete full length crosscut. The second example I want to show you here is what happens if you use materials that are heat sensitive. So and it's only the right picture that is important here. And the right picture shows a cross-sectional view of a inkjet printed silver nano ink particles that has been printed on an inkjet paper. So the dark piece on the right image here, that is the surface of the paper, and we can see the ink track. The ink track is like 500 microns wide or something like that. And this gray area, that is the cross-sectional view after it's been milled with this machine. And we can see that these inkjet papers are very complex papers. Actually, it is a layered materials of ceramic compounds and soft plastics and things like that. And then we have this very heat sensitive silver nanoparticles. So if you heat them up above 100 degrees, they start to sinter. So what actually I want to show you with this picture is that this is an awful result. This machine cannot deliver good results on this because we have a hard material on the paper that need high power to be able to cut it clean, but we have a soft, delicate silver nano ink that is very beam sensitive, so that doesn't mix up well, so it destroys the results for us. The left image shows how the image would look like if we make what we would like to see in the image. It's a different scale here, of course. It is a highly magnified image, but the left image is made by ultramicrotome instead. That is the only tool that you can use for this particular application. The last example I want to show you here is instead of a paper cross-sectional area, here we have a completely different material. So this is a graphite graphene mixture electrode material that contains silicon particles. So this is used for lithium-ion battery technology. So, and here we can see that, of course, this graphite electrode material is very porous, but that doesn't mean that the machine cannot handle it. So it depends on how the porosity, the size of the pores is, and how much of the surface, how rough is the surface when you have it against the titanium mask. So this is a typical example that you can achieve very good results even if you have high porosity in the material. And this material contains both graphite with this, what shall I say, semi-hard in this technique. It is harder than paper, of course, but it's less hard than silicon particles. So the bottom right image here shows you a magnified image of the cross-sectional area, where we see in the center here, we have one of these silicon particles that has been completely cut straight through by the argon beam. And we see also the graphite flakes around it that has been completely cut through. So I think this is like I will have this as the final image and the conclusion of this technique, showing that the material that we see here, the porosity of the electrode, all that has not been mechanically deformed at all. We actually see the porosity of the electrode as it is when we created the electrode. So we can really see how well this silicon particle is interacting with the surrounding graphite. So if you have these kind of research questions, this technique is very useful for that. So, and I think that concludes the broad ion beam talk here. And then now I will leave over to Börje to talk about his XRF technique.
Thank you so much, Magnus. Really good presentation, and at least for me, it's one of my favorite topics because I like this equipment and I use it quite a lot. Also, previously especially used. Let me ask the audience if there is someone who has a question. If you have it, you can raise the hand. You can post it in the Q&A. You can also post it in the chat. So maybe we should go ahead with the presentation of Börje, and then we can take the Q&A after the both presentations, right? I think it will be the most efficient way to proceed. Good, great. And now I can see that Börje having the slides on. So please, Börje,
Yes.
The floor is yours.
Yes, thank you for inviting me to this seminar. I will talk about this custom-made imaging that we are looking at Treesearch for XRF material mapping imaging. This picture I show right now is an XRF image taken by Argonne National Lab in the US by Barry Lay. So it's collaboration there where we look at some wood fibers and we see the color scale shows the sulfur component, so we can see how it's distributed within the fiber. But I will continue with the technology and the idea about how we work. So the outline of my speech is that I will say a little about my research group, Radiation Sensing and Imaging System, why we are working in this field, and then I will explain the difference between absorption imaging, XAS, and XRF, fluorescence imaging, and I will provide a few examples and then discuss the prototype. I will also discuss a handheld XRF measurements and the prototype for sulfur X-ray imaging in wood fibers, this starting image. So we have been looking at this for about 20 years, and to get it initiated by CERN, but we were a partner there, and Christer Freud was initiating a conference series called IWARID, that for imaging, X-ray imaging, and I have a patient here when I started my PhD, and I think this is the first color X-ray image for dental purposes. I'm a little careful about talking about that, because astronomers have been doing color X-ray images since the last century. So, but here I looked at waiting for so I looked at how the image actually changed when we are changing the energy of the received image. So I'm going to continue about how we can use this. For this purpose, it was contrast versus dose study, but this to see how you could minimize the dose to the patients in the European Union and still have a reasonable image quality. But there is a lot of different things you can study with this technique. And if I mention this collaboration then, so the Medipix Collaboration, it's a platform for development, for detector development, for the application of X-ray material mapping. So it's hosted by CERN, that I assume that you are aware of, well, the biggest international physics lab. And this project has a little bit more than 4 institutes in collaboration. And it was initiated in 1997, and now it's in the fourth generation. And Smith Sweeney University has been a part since 1999. So you can contact CERN. For knowledge, if they sometimes, usually they refer back to us at Mid Sweden. I want to go a little more into examples on how we actually do these images, and I want to compare what I call transmission and reflection. I hope there is no one from physics that's listening. Well, Magnus is listening. Transmission is the correct term. Reflection is not the correct term here, because if you're doing transmission, you're shining through its normal X-ray image. But from a practical perspective, if the sample is too thick, then you cannot transmit through it, but you can still look at some of the reflection image, which is not a reflection in the physical term, but it's I will go into come back to that later. But the transmission image is usually referred to as XAS, or X-ray absorption. And in this view here, I have some red and some green parts of the sample, and then you want to try to image it, and you need a spectroscopic detector so that you can resolve the different parts differently. And or instead of a spectroscopic detector earlier back in medical imaging, they started to diagnose brittle bone disease by running dual energy, essentially put 2 voltages on their X-ray source and try to did something of this type of imaging or distinguish, and they got 2 different images that they could subtract. And but what we have been looking at is spectroscopic imaging in the detectors. If we have the other type of setup, then you can do the images by, most common I think is to do image stepping, where you have a very narrow beam like a synchrotron beam, and then you step through the image. But you can do this in different camera modes, like a pinhole camera or straight polycapillary optics, like I drawn here. You need some optics because otherwise it will be a blur of the image. So if we let's look at what's happening when the X-rays are meets the sample. So the X-ray photons will penetrate the beam. That was or the sample. That was one of the ideas of X-rays, but there still happen things. You get electrons, Auger electrons and photon electrons that are excitated, so you get them out. You get fluorescence X-rays and you get X-rays scattering. But for the transmission part, we look at the transmitted X-rays, and then the type of imaging here we can say is K-edge X-ray absorption. You can look at different processes, but if you assume and think about that the photon is passing through, and then you get you kick out the K-shell electron, and then you need a photon with the energy above this binding energy. And if you cannot, if the photon cannot interact, then it has a higher probability to be transmitted through the material, and that gives us this type of spectrum that we have when we increase the energy, the Lambert-Beer law says that we have a higher penetration, or a higher probability of penetration. But then when we reach the K-shell binding energy here of sodium, then we get the shift down. So we get the material recognition here that we have sodium in the sample, and here I took 2 thin foils of sodium and sulfur put it in a simulator, and then we see the continuation here. We got the edge here, then we see the continuation, and then we reach the sulfur K atom binding energy, and we get the same effect here. And I studied this for a few samples some time ago. I looked at this previous spectrum was ideal if we have an X-ray spectrum, an X-ray source. It's not a white spectrum. It will not be ideal in a similar way, but we will get different shifts. So here I had a sample where I looked at some medical tracers. Iodine and gadolinium are common tracers, and then tin, soldering tin, you usually can find in an X-ray lab or in an electronics lab. So I took some part of that also, even if that's usually not a medical tracer, and looked at a theoretical image what we actually could make here, and what it should be if we have this X-ray source. And then we had the system, the Medipix system, and I actually built a detector for this one. So with 220 micrometer pixels, and I got some help from a student in Freiburg, from Albert Ludwigs Universitet, to do the bump bonding of my detector to the system. And we got some quite early images of these different samples. The tin sample is a little too thick, it gets a little black, but you can see that you still have this type of color. So I made an RGB mapping of these samples. And then to demonstrate that it's possible. And RGB, it was a shifting, it was just taking the spectrum and correlate them to a visual representation. You can there are more advanced material mapping schemes. I just take a little bit looking out at what's development in progress. I'm waiting for my computer to change slide. But this is something that is going on for tomography imaging, where you want to make a 3D reconstruction. This this work is continuing, and there are projects with a Mars project in Australia, and some other aspects. Do you still have picture?
We still see your slide with 3 images.
Yes, my PC says that it wants to restart PowerPoint.
Oi.
I try to do that then. So I'm sorry for the inconvenience.
No worries. In the meantime, I want to remind all of you guys who are listening to not be shy and put your questions in the chat, in the Q&A, or raise your hand and just ask them. And these are the questions both to Börje and to Magnus also. And then also this webinar, it will be available later on the Treesearch website and also on our YouTube channel. I will put the links also here in the chat, so feel free to share it with your colleagues and watch it on demand later on.
So let's try to share again then. So
at least I can see the front slide now. It works.
yes, and okay. Yes, I was into describing that you can map in these transmission images, you can map the different materials, and I see that SAN has put the development online, so I was just thinking to share with that they're one of the partners in the Medipix Collaboration are developing a CT machine for this 3D reconstruction. For the paper industry, I think that 2D is probably more useful, but it depends on the on what type of material properties you want to study, and of course the 3D viewing can be there can be quite much for the understanding of material properties when looking into that. I want to come back then to the different parts, what we can look at, and look at the other way to study images, and that's to look at the X-ray fluorescence coming out, and that will be quite much of a surface measurement, at least for more dense material. For paper material, you will have a depth interaction there, but the principle of X-ray fluorescence is that you irradiate the materials and you will kick out this electron, so you need to have a higher energy than the binding energy of the photons, and then to fill the place of the K-shell electron, or the L-shell electron, you need one electron coming from further out to fill up this place, and then you will have a characteristic photon that will be emitted when the electron falls to a lower energy state, and this is quite common, this type of handheld instruments, since it is a non-destructive way of analyzing. So if we so for every metal, like here for a copper atom, then they will have a very characteristic peak of the energy difference between an L electron and a K electron. And if we then look at the periodic table, we can have a lot of electrons that we can essentially identify them all. But helium number 1 and 2 is not that easy because they only have K-shell, so we don't have this transfer. And then up to sodium, we have a problem that the photon energy of the characteristic photons are so low, so they get absorbed in air. If you can try to be very close, but it's you lose quite much of the signal. So this type of measurements, if you should do this measurement, it's most efficient to do it in vacuum. I was thinking that we can have a look on just on a handheld instrument like this. If I stop share momentarily, and if we try to analyze something, I will try to now the video is spotlighted. So I want to just show the instrument, and so this is possible to use to buy them, and we can try to see what I can. over here. And if we try, this is well, ring with the logotype, with the university logotype from Silver Clue artist in Östersund. If we try to take a sample of that, try to get it. I have a little difficulties in oh yes, now we got it. So if we just try to, maybe not that easy to see on the screen, but we got 75% gold and 15% copper, 8% silver. So it's just an example of that. This is very popular for metal sorting and this type of imaging. And if you think that you can have that, you have a application where you need to do some kind of quick metal analyzing, then maybe handheld instrument is good, and we from Mid Sweden, we can help. You can try this out, and you can buy them from the different provider. There are a few brands available, but there is it's a quite simple to use. What you should be a little bit aware of is that you should not, I was using it at the table now, but you should not run it through the table like this, because then you're X-raying your legs. So you need to, if you have a tree table, if you have a steel table, it's you can work it like that, but it's you need to think about the radiation, some radiation safety. I continue to share my way to share my screen, and I think I continue to share my screen. So, and this is a more complicated spectrum. This is looking at, this is also paper related, but it's the fiber bank material that we have been looking at, analyzing, and this is my colleague Faisal has done these imaging using the handheld instrument and some sample preparations on the drying. So we can see that we have quite many elements. It's quite, but you still can use the technique to distinguish a lot of elements. And if you want to do the imaging also, then there are different properties, and the picture I started my presentation with was a scanning image, but done at the synchrotron. But there are possibilities to use an all-type pinhole camera. So you radiate the object and use a pinhole to get an image. This is done sometimes in archaeology and artifacts to study old paintings, and we have also looked at fluorescence imaging with straight polycapillary optics, where we have a bunch of fiber optics essentially, so that we get we get a reflection, or we get a waveguide for these X-rays, and using that we have actually been viewing a Eurocoin just to see that we actually can distinguish this nickel brass where we have zinc from the copper and nickel in the middle. There is copper and nickel in the outer layer also, but we have where, depending on how we set the energies, we can actually try to image the ring using the Medipix 3 device, or the time here is, and we I wanted to look at the scanning example also. So here is another different application where we looked at XRF, at the XRF response for the coating quality for paperboard. So this was done in collaboration with Mora Research, and it was a project with Iggesund, with Holmen. And if we then X-ray the sample and start to move it, then we need one spectrometer, and we can get a signal out, and then we can reconstruct this to an image. We had to work a little with the shielding to get this to work, and then a spectrum could look like this. So here we have a strong signal of calcium that comes from the coating. So that's good, it should be there. So we have the K alpha and the K beta line. Then we also got iron from the mounting, so that we try to suppress. And we say when we're in the radiation lab, we need shielding, so we have lead, and it comes there. And in the end, there was argon. Should there be argon in paper? Well, that's a little strange, but we cannot get rid of argon because we have it in the air. So it's we see it. We do not see the air because we have here somewhere is a limit for this for the spectrometer. And in this study, we looked at reference image taken with common chemical burnout process, and we compare that to an XRF image here with it's quite wide steps. It's 0.5 millimeter, but if we interpolate it, you got a quite nice agreement with the actual sample with so we got the view about how the coating quality was. And we have the recent project we have looked at is the CTMP pulp, and the possibility to can improve the pulp by by looking at the chemical, to have an even distribution of the sodium sulfite, so that we in the impregnation, so that we get even impregnation, even if the wood chips have different lengths, fiber widths. The amount of sulfate groups bound in the fiber, or more specifically to the lignin in the fiber. So we need to, we can measure them with the different other ways, like conductometric means. But the challenge is to see the inner part of the wood chips, and if they accept a lower sulfonation degree compared to the outer part. So the setup we have built are a stepping imaging setup where we use titanium as mounting material to not disturb the energies of interest, and we put our paper sample into the setup, and we have helium atmosphere in the box, and then we have stepper motors to move the machine or to move the sample. And if we tested with a simple, just a nickel foil, some paper, and some copper wire to see that we can achieve imaging. And what we got, then if we just highlight the parts of the spectrum where we have the nickel, the copper, and the sulfur, so then we can see that we reproduce this. And this is done with a pinhole collimator, but we did not achieve the setup is still a little rough in resolution. So the next step will be to buy polycapillary focusing optics, where we use an X-ray lens to improve improve the spot and get it down to a resolution of 10 micrometers. That's what we're aiming for, and this is in the process of purchase. So I'm in contact with 2 companies, 2 possible providers to purchase this. It has been slightly delayed by the Ukrainian crisis. Actually, it has been, but it's an American company, but it so I am, or a German company. So I will hopefully have some results quite soon. And I want to end with thank my colleagues that have that are consisting our research group. So thank you a lot for listening, and I'm happy to answer questions.
Thank you so much, Börje. Really great presentation. I'm quite new to the topic of XRF, but it was really interesting to see how you can do the measurements IRL, you know, like using your ring and then literally taking the measurements. We didn't see that much on the screen, but we trust you.
Sorry, I should have.
It's okay. But I mean, like it was really nice demonstration actually, how it works and how it could be used. So the audience, you have a chance now to ask if you have any questions. Otherwise, I think I can go ahead with the questions. So Börje, I wanted to ask your opinion about, like, I see this approach as a very feasible and very suitable for the paper and packaging, right? So do you have maybe some industrial application cases or some experience? So like if you would put it in the simple words, in one sentence, in which case you would use XRF instead of other measurement techniques for the same, quantification chemical purposes?
What I am, where I think XRF can be suitable is where you want to have something actually online. So like these handheld instruments, they are, I mean, one problem for the companies selling them is that they try to make them very robust because they sell them to this metal recycling companies, and they are not careful with the instruments. So I mean, but the technique has the possibility to actually work in an industrial environment. So what I see as a possible application is actually to have this as an online instrument. Then paper industry, the conveyor belts and so are quite fast. So it's somewhat of a challenge to get it fast enough. But there are companies that are more into the speed, and I have had discussion with Hamamatsu, for example, about how fast you actually can make the detector.
So in principle, it can work nice even in the QA/QC line for the industrial production, which is actually quite unique. That's really nice. Because, I ask these questions since I never hold the equipment in my hands and, I never tested it, but it was really nice to see how it works and also listen about the scientific explanation, how it works. So any more questions to Börje, guys? Last chance? No? Good. Then I have a question to Magnus, actually. And Magnus, really great presentation, really great overview. I know about the broad ion beam more than about XRF since, I worked a lot with ion beams myself. And I want to ask your opinion about the level of the artifacts that one is getting during the cut. So my subjective opinion that if we work on the macro and micro scale, then it's something that we can definitely tolerate and we can get the nice smooth cut and we can see even layered structures. But then when we go to nanoscale, that's the level where we get the problem. So if we maybe can talk about the scales, for the paper and packaging, what would be reliable?
Well, the artifacts of the system is the two types of artifacts, you can say. When it comes to a solid surface, the surface will have basically no artifacts. It's almost atomic flat. You could see some more macroscopic waviness that can be introduced in the surface, but that comes from from the mask basically. So if you have a strange texture in the mask is it is a macroscopic polished solid titanium piece. So small structures in the mask will be copied over to the surface, so that it can create some waviness. But that is usually of less concern in microscopy business because you work at a much higher magnification, so you don't really see that. So it is atomic flat and very nice to study at high level of magnification. But one artifact that could be introduced that you can see is you can get these deposits of milled off materials. So and one common deposit is from the titanium mask itself, because even the titanium mask will be degraded down over time. So you're removing titanium materials from the mask, and that material will be deposit onto your material. So if your material is a solid homogeneous piece, then that is of less concern, because then that deposits will be on the back side of the surface that you will not investigate anyway. So then you will have no problem with that. But if you have like a porous material, for example, this composite electrode material I showed you, depending on how the material reacts with the beam, you can get these deposits into the pores of the cross-sectional surface, and that can be more or less a problem, and it directly links to the porosity. So if the porosity is very small, then this is usually a small problem.
I would add one more. That's if we talk about the nanoscale, yeah, and usually in the wood-based materials, we should see nanofibrils.
Yeah.
But then when we cut with an ion beam, at least on the nanoscale, we don't see those nanofibrils well isolated. So
well,
they are.
I have done tests like that, and it worked out very well actually. And there was some partner company that made some studies regarding this. They had some nanofibril stuff inside the paper, so it was like a complex structure. So they were freestanding nanofibrils embedded inside this this default paper, right? So, and when we made this cross-section cut with this miller, you could actually see that some of these fibrils that were free hanging inside the paper, the macroscopic paper structure, were just nicely cut in half. So you could see the cross-sectional area of the fibril. So I never seen any performance like that on some other technique, because the smaller structures you have, if you introduce some mechanical stuff, right, polishing, microtoming or something like that, you bend these things. But this turned out very well. So,
no, that's great. Maybe it was, I don't know, did you use cryogenic temperature or?
No, you cannot use some cryogenic stuff. What do you mean by microtoming? Or?
No. I mean, like what we did, we tested quite many different broad ion beams. And actually you can do the cutting at the cryo conditions. So you can freeze the samples also.
Yeah. But then you need that. Well, yeah, we don't have that.
You don't have it.
We cannot cool the samples.
I see.
During the cutting procedure. So this was just done in normal procedure. But I mean, everything boils down how the sample looks like. I mean, this was one study. It was very successful in our case.
That's great.
But there are many versions. So I think that is one drawback perhaps with this machine, is that all samples require their own unique recipe.
Yeah.
So there is a lot of trial and error before you figure out the parameter that fits your particular sample. After that, it is a smooth ride. But the first part, figuring these things out, can be a very tough role.
We have done the test on the delignified balsa wood. And we have tested pretty much all of the different machines from different suppliers, the broad ion beam. And we did quite systematic studies, both varying the temperature, the energy, the dose. And maybe we had really quite high standards and requirements, because the tiniest nanofibrils, they will be like down to 4 nanometers in the width.
If it is this super tiny nanofibrils, I think you are doomed. I mean, you can't even monitor them in the electron microscope. I mean, they easily burn even there, even in our low current. Exactly. Because we know how the fracture surface or the microtome surface would look like. So then at the end, we use the ultramicrotomy to slice them and to cut them and to see the nanofibrils organization in the cell wall structure, both for the delignified balsa wood and, for instance, also in the transparent wood, where the wood was used as a template and impregnated with the polymer. But unfortunately, with the broad ion beam on that level, we were not able to get the tiniest details, since the surface was altered and the
fibrils were no longer isolated from each other. It was like a nice smooth surface. But on the micro scale, we got amazing data, really, really good. So it's like, you know, we could do the porosity studies and also, you know, like analyzing the lumens and yeah, distribution on the micro scale. It was really good. The same also for the paper and packaging. When we cut was a broad ion beam. The data that you showed and the data that I also saw somewhere else, it's really nice lamellar structure that one can get. And usually for these samples, it's quite difficult also to get that information. You can't just, you know, simply cut it with the scissors. You need to be more sophisticated. So I see this approach as a very, very useful approach for the sample preparation, but there are limits. So like maybe not for the true nanoscale.
All techniques are complementary, right? I mean, for this fine detail works, the focus I-beam is of course a better tool. It is using less power also. So
yeah.
You basically need all the tools.
Yeah, exactly. With the focused I-beam, we have a problem with the gallium ions. So sometimes then using
but there are different focused ion beam systems also. This gallium thing is that is the brute force system, right?
Yeah.
There are more gentle beams that you can use also.
Yes, and I can see a question now for wood or wood fiber in FIB. Do you embed samples in resin, or what are the sample prep challenges? So depending on what kind of samples we're using. So for instance, my colleague Cecilia, when she was cutting just wood fibers in Chalmers, she didn't embed them at all. So she was, slicing as they are. And then, so from my experience for the focused ion beam, we didn't do so much embedding for the wood-based materials. When we were, for instance, working with the biological samples, then yes, we embedded. Oh, now I can see that our colleagues from NXT Gen Wood, they have helium ion beam. So that's excellent. Now we know where to go to use the helium ion beam. I'm reading the chat. So that's why,
much better than your gallium tool for this particular.
Exactly, yes, because gallium is so heavy, but gallium is so widely spread. So basically the focused ion beam technology started from it. I did 7 years of work with a focused ion beam, so that's why, yes, with the FEI.
Regarding this wood fibers and things like that, that is, as you said, usually you can cut it just straight on. But there is a problem. Well, it's not a problem. I can rephrase it like this. It's most of the time when people want to study wood fibers, they tend to become even larger samples, right? I mean,
exactly.
It starts to become at even lower magnifications that you're going to start. So that usually implies quite thick cross sections.
Exactly.
And a thick cross section, that is not so nice with these broad ion beam techniques. I mean, I have not tried making some kind of insane thickness, but I will say that the limit is around 1 millimeter or something like that. If you want bigger pieces, the thickness of the cross section to be larger than that, then it's I assume it will start to look really ugly. Yeah,
with the focused ion beam, it's even smaller.
That's a different story.
So that's another limiting factor, but still these techniques, they could be used, yes, which is really nice. Good, and nice discussion, and thank you, Colm, also for your hints and description in the Q&A. I think we don't have any more questions for today, but I would encourage all the participants, all the listeners that we have now online, and also people who will watch later on demand, to not be shy and contact us directly if you have any questions. So if you have questions in general about research infrastructure, research, you can talk to me. If you have questions to the specific nodes and specific instruments, you can talk directly to our specialists and to coordinators. So for instance, if you have questions about XRF, please feel free to talk to Börje directly. And if you have any questions in general facilities that are available at Midfield University, please talk to Magnus. So it's not only about broad ion beam, but it's also different electron microscopes and atomic force microscopy and other facilities that are available. So I really encourage you to contact us. And the beauty of reaching the specialists through the Treesearch network, that for all of you who are associated to Treesearch, you can get the financial support for performing the measurements and analysis, and also you can get more speeded up access and high-end competence, which is usually, yeah, something that we're hunting for. It's not only about pressing a button, it's about how to analyze the data. With this, I would like to thank Börje and Magnus. Thank you so much for the great presentations today.